Okay, so last week we worked on an example, speed control of a car. So we spent the entire week on that example. So I would like to make a summary of that example before I proceed with feedback control. So that example is a simple problem, but I think it demonstrates a lot of the things we've done in this course so far. Okay, so this is from last Monday. So last Monday is the time when I first defined this problem. And then, so this was the block diagram. So let me just start the summary from here. So it has the following block diagram. Let me just copy it from here. So there are two inputs and one output. One of the input is the gas pedal position. The other input is the external disturbance force. And the output is the speed. Because the system has two inputs, one control and one disturbance, and one output. The transfer function matrix was obtained as, okay, so this was transfer function matrix. So the key inputs are these, and then so they change the output through this transfer function matrix. So let me just write this as P times theta of S minus G times FP of S. Or I can take G out of the parentheses and write this as, and G was 1 over ms plus B. Okay, so first we studied open loop control, right? First, we studied open loop control, assumed theta to be a step signal, and found the step magnitude to reach a certain target steady state speed. Okay, so before this, actually, let me the steady state output for this problem was, if we use the final value theorem, Okay, now we can apply the final value theorem, and if you do that, okay, so this was the steady state. So this should be steady state value of the speed. Let me write it VSS. And while doing that, we ignored the disturbance input. So let the desired speed be Vd. Then from here we said that the gas pedal input magnitude should be equal to B times Vd divided by Ke. Okay? Okay, so and then we tested the performance of this control strategy under different conditions. In fact, we considered two specific cases where there were some disturbing effects. Okay, so and one of them was the case where the engine performance was not ideal, and the second one was the case where there was an external disturbance with so basically the car was climbing uphill with an alpha, non-zero alpha. Okay, so let me just add these as well. Okay, so we tested the open loop bu arada şu araya bazen çizgi konuyor ya, onunla ilgili de bir kural varmış. Onu bazen mesela open loop derken araya çizgi konuyor, bazen konmuyor. O da çok basit aslında. Şimdi bu kelimeleri ayırıp tek tek kullanmak mümkünken araya çizgi koymuyorsun. Ama tek tek anlamsız oluyor. Sadece birlikte kullanıldığı zaman anlamlı oluyorsa araya çizgi koyuyorsun. Yani mesela burada şu çizgi koymasak loop control strateji çok mantıklı değil. Yani ya open loop'tur ya closed loop'tur. İkisini birden söylemeden anlam kazanmadığı için araya çizgi koyuyoruz. Open loop control strateji. So anyway, we tested the ya dolayısıyla mesela şurada konmuyor. Mesela şöyle desek tested this in open loop. Burada cümle bitti ya. Ya buraya şunu koymaya gerek yok. Çünkü o bir tamlamanın parçası değil. Open loop bitiyor. O yüzden ya bazen çizgi oluyor, bazen çizgi olmuyor, bilmiyorum. Sizi hiç rahatsız etmiş miydi de. Ben doktora yaparken Georgia Tech'te bir oda arkadaşım vardı. Amerikalı bir çocuk. Çok da iyi bir çocuktu. Yani hem olarak ne derler, meraklıydı böyle İngiliz dil bilgisine vesaire. Normal bir Amerikalı mesela bilmediği bir sürü şey biliyordu. Biz onunla böyle gece gündüz yan yana çalışınca çok oluyordu, faydalanıyordu. Mesela her şeyi soruyordum, bu nasıl yapılıyor falan diye, o bana açıklıyordu. Böyleyken böyledir, böyleyken şöyledir. Bu da ondan öğrendiğim bir bilgi yani. Kulakları çınlasın. Open Control Strategy. We tested Open Control Strategy. We obtained the following results for Vd is equal to 25 meters per second and theta 0 is equal to 1/2. Okay, so now let me make a table. Okay, so when we get this table, you will be able to see all the results at once. So the first one is the actual engine constant. The second column is road disturbance, or let me just put alpha, road inclination. And the last column is this actual steady state speed. Okay? Okay, so the first case is the ideal case. Okay? In the ideal case, engine constant is equal to what we expect it to be, which was 12,500 newtons per just newtons, I think. And the road inclination is 0. So this corresponds to the ideal case. And for this, the steady state speed was 25 meters per second. And this is exactly the same as our target speed. Okay, so the target speed was achieved without any errors. And the second case was the road inclination was still 0, but the engine constant was 10,000 instead of the expected speed. Okay. So when you put that number into this equation, in fact, we can do the calculations very quickly here. So the K is equal to 10,000, alpha is equal to 0, and I can find the theta 0 is equal to 1/2, and the rest is there. So if I click this, oh, I didn't change the KE value, so the KE should be equal to 10,000. And the final steady speed of the car turns out to be 20 meters per second. So obviously we lost a lot of performance. We were expecting to drive at 25, now instead we're driving at 20, so that's obviously a bad thing. The second thing is, let's consider alpha. So let me make alpha is equal to 5 degrees. And let me make KE equal to the original value, 25.58. So for this, the final speed is 21.58. And then as the last case, let's consider both the engine is bad, for which KE is equal to this much, and there's some alpha, 5 degrees. And the final speed for this case is 16.58. Okay, so this table summarizes all the simulations we've done last week. Okay, so the results above show that the open loop control strategy works fine under ideal circumstances, but when there are when there are effects that are not accounted for in our mathematical model, the performance degrades very quickly. Okay, so that summarizes the open loop control. Next, we will consider closed loop control. Control with the simplest controller, which is a static system with transfer function equal to a constant number k. Block diagram for this case is okay. Now let me just find the block diagram from last week's notes. Okay, so this was the block diagram. So this is the controller transfer function k. Now there are still two inputs, but the control input is now V as desired instead of theta. The transfer function matrix is so this is a transfer function. Okay, and so to check the performance, we consider steady state speeds, right? So let me just tell you what the steady state speed is for the closed loop case. If Z is a step function, and again the FP is the same, then steady state error becomes not steady state error, steady state speed. Okay, so now let's make the same table with the closed loop case. Okay, so now let's test the closed loop control with. Okay, so to find some numerical values, we need to choose a value for this k number. So let that k number be 0.1, and we as desired be 25 meters per second. Okay, so now I'm going to calculate these numbers for different values of alpha and Ke. Okay, so I start with the ideal case. So let me make sure that Ke is equal to the ideal number and alpha is equal to 0. And now I need to calculate this quantity. Okay, so this is that quantity. So Vd is 25. mgc now divided by B plus K times Ke. So the value of this thing is no, K should be 0.1. Okay, so 20.83. Okay, so if you are following what I've been doing, at this point you may say that I thought we were expecting the closed control to be better. How come it is worse? Right? Because even under ideal conditions, the actual steady state speed is not what we want it to be, right? Because we want the steady state to be 25, and yet even in ideal conditions, the steady state value is less than 25. Okay? But that is the result. So anyway, let me complete this table. So let me change the value of Ke to 10,000. For this, the value is 20. Okay, it is there. 20.26. And as the last case, $19.32. Okay. Takip ediyor musunuz arkadaşlar? Hı? Daha kötü oldu değil mi? Well, okay, so you're right that the performance is worse, but what has changed is the following. So let me just write this and doğru, o da kısaldı ama on şimdi sadece steady state değerlerine bakıyoruz. Now even under ideal circumstances, the car cannot reach the target speed. This is because the static control system we used with G sub C is equal to a constant number is not good enough. But what is important in above results is that the effects of the disturbances are smaller compared to before. So to see that, let me add another column, and we call this percent change. So this is the ideal case. So for that, let me make this one. So this 20 is so the first disturbance causes an 80%, make the output 80% of the output of the ideal case. The second one, and the last one, 66%. So now let's find the same numbers for the closed loop case. So if you call the first one one, the first case is 96%. The second case is 97%. So the idle performance is bad, but these disturbing effects has a smaller effect on the total output, total results. Okay. So here, if you have both an inclined rod and a bad engine, then the performance is 66% of the ideal performance. But here, when you look at this case, it's only 93%. Okay. Now, let's try it with a different controller design with k is equal to 1 instead. So remember, in this table, the k value was 0.1. Okay, so now let me change right now it's 0.1. Let me change it to 1. Okay, so let me go back to the ideal case. It's 24.5. See, this time it is much closer to our target speed. So let's calculate these other numbers as well. So if KE is equal to 10,000, 24.39. Okay, so this is the last case and result 24.3. Okay, so I think these results are much more impressive, right? So by changing the controller So this is what we changed. We made the actual state speed in the ideal case increased to 24.5. Now this is very, very close to our target speed of 25. But now what's even more important is, so these disturbing effects are now much less important. Okay, so even when you're climbing a hill with a dead engine, you can still reach the 99.2% of your ideal speed. Okay, so I think this example is very good in showing the importance or the power of closed loop control. Okay, any questions? Okay, so yeah, so comparing these last two cases, it's very clear that the value of k is very important. Okay, so first we tried 0.1. So this is where the old expertise lies. So the control engineer. So all our job is actually finding these numbers, finding good numbers that define the controller. So that's the only thing a controls engineer does actually. So if you can shrink everything down to finding these numbers. So we call that controller tuning. So you try different numbers, and in all cases it boils down to trial and error. But obviously there are some rules. I mean, you don't guess numbers arbitrarily. So there are things that you do to see what numbers should be chosen. So you start with those numbers, and in the end, when you are testing it on the real system, you change them a little bit by trial and error. You increase them, you make them smaller. But that's pretty much summarizes a controls engineer's responsibilities. Okay, so we started with a gain of 0.1, and then we tried 1, and obviously a value of 1 works much better, right? So these numbers are very, very close to the original number, and the ideal case number is very close to the actual speed. And if you increase it even more, so let me just quickly show that too. So instead of 1, if you choose 10, for example, then so let's just try the worst case. So this is the worst case, 24.9. So this number increases to 24.9, and in the ideal case, this is the ideal case, it's 24.95. See, these numbers get closer and closer. Okay, so as I said, finding the right number is the only thing actually. So that's the controller design. Okay, now I would like to show you some interesting thing though. So according to here, if you choose an even larger number, so why don't, if choosing large k is a good thing, so why don't we make it 1,000? Then you will see that in that case, your car will be able to drive at the same speed no matter what. So it doesn't matter whether you are climbing a hill or your engine is not working as expected, you'll be able to reach that speed. So obviously life cannot be that good, right? It's not, there should be something wrong here. So, and now let me show you what is the problem with choosing a large k number. So obviously making k large improves the results. The output in ideal case gets much closer to the target's output, and also the effects of the disturbances get smaller as well. This trend continues, and as we make k larger, the results get even better in the case as k approaches infinity. Becomes equal to 25 for all cases. Unfortunately, there is a downside for choosing large k values. Ya bu mühendisliğin her tarafında böyle, yani hayatta böyle aslında, yani şey yok, ne derler, hani bedava bir sonuç yok. Bir şeyler iyileşiyorken bir yerler bozuluyor. Ya burada da öyle. Ne zaman böyle şey olsa, hani when you obtain a result that seems too good to be true, in most cases it is too good to be true. In fact it's not true. Fakat ben bu yaşıma geldim. Hala arıyorum onu. Yani hala böyle heyecanlanıyorum mesela. Hatta geçen hafta falan olan şeyler bunlar. Bir şey oluyor. Diyorum oldu işte. Harika, mükemmel şey buldum. Bir yerden bir patlak verdiği ortaya çıkıyor. So let me show you that problem for this example. So by the way, while showing what the problem is, I'm also going to show you an example for choosing different outputs. To see the problem with large k values, let's consider the gas pedal position theta as the output of our system. So I choose theta as my new output. So I should be able to write the transfer functions from these inputs to that output. So from these two inputs to the new output theta. New output theta. Okay, so let's just give a break and I'll work on this and I will show you the results when you come back.